This is section 9.6a, permutations and combinations. First, let's talk about counting possibilities, or counting the number of possibilities for various events. And this is a good example to illustrate what we mean by counting possibilities. How many different pairs of letters chosen randomly from the alphabet are possible? And repeated letters are okay. All right, so this is just to count how many different possibilities there are. So AB, for example, is a possibility. XY is a possibility. CC, DE, BB, AN. All right, you get the point. What are all the different pairs of letters, the different possible pairs of letters? Now, I want you to take a minute to try to think about this on your own. And pause the video, try to do that, and then resume if you get stuck or if you get what you think is the right answer. So this is the answer. 26 times 26 equals 676. So there are 676 different possible pairs if I'm choosing letters randomly from the alphabet. And for this particular case, repeated letters are okay. So AA, BB, KK, those are all valid pairs. Why is it 26 times 26? Because if we look at this first number as an event and this second number as an event, well, I have 26 different possibilities for the first event and 26 different possibilities for the second event. And for any one of the possibilities of the first event, there can be 26 that go with it. So it's 26 times 26. I have to multiply it by all the different possibilities. So let's consider M and N independent events. For example, in the last example, M would have been picking the first letter, and N would have been picking the second letter. The fundamental counting principle states that if one event can occur M ways, and a second event can occur N ways, the number of ways the two events can occur in sequence is M times N. And we saw that illustrated in the last example. This is just kind of saying it in general terms. So let's look at a coin toss. If we have our first coin toss, we know there are two possibilities, heads or tails. Two ways to flip the coin. And then let's say that I toss the coin again. So I got my result, whatever it is, heads or tails. And then after I get that first result, I toss the coin again, and I can get heads or tails if the first one was heads, and I can get heads or tails if the first one was tails. So there are also two ways to flip the coin. There are 2 times 2 different outcomes, 4 different outcomes, HH, HT, TH, TT. So let's look at this. If my original coin toss results in H, as you can see where the arrow is pointing, well, then I can toss the coin again and get either H or T. So following one path, I get H, H. That's one possibility. And you can think of that as one path, HH. Another path is HT, HT. Another path is TH, TH. And another path is TT. And I can see here visually that there are 4 different outcomes, HH, HT, TH, TT. And mathematically, it's just because there are 2 different ways to do the first event, 2 different ways to do the second event, and 2 times 2 is 4. Another example, a meal consists of a main dish, a side dish, and a dessert. How many different meals can be selected if there are 4 main dishes, 2 side dishes, and 5 desserts available? This might remind you of that problem we did for SAT practice, of all the different ways you can travel from one city to another. Remember when there were different stops along the way, and you had 3 different ways to get from point A to point B, and then 5 from point B to point C, and then 6 from point C to point D, etc. So this is similar to that if you remember it. But even if you don't remember it, you should have enough clues to be able to figure this out on your own. So pause the video, try to do it, and then resume when you get stuck or when you have an answer. All right, so let's go through it. Number of main dishes is 4. That's given to us. We multiply that by the number of side dishes, which is 2. And then we multiply that by the number of desserts, and that's 5. So my answer is 40. That means there are 40 different meals that can be selected because there are 40 different possibilities. For each of these main dishes, if I pick one main dish, well, there could be 2 side dishes that go with that, and for any of those side dishes there could be several different desserts. So this is the way mathematically to count all the different possibilities. Now you could do it by hand and just write down all the different possibilities, but that can be time consuming. It's better if you just remember the mathematical way to get it. If number of main dishes is one event, number of side dishes is another event, and number of desserts is another event. These are 3 independent events. And so m times n times p, if you want to call the events by those names, m times n times p would give you all the different possible events. All right, so hopefully this is becoming a little bit more clear. I know that it's a little bit hard at first. Usually students have difficulty with counting principles and probability, which we'll get to in the next section. This is really the first step of probability because you need to figure out all the different ways something can happen, and then later on we'll build on that to find probabilities. For example, let's say that you have 4 main dishes. Let's say that's one's chicken, another's beef, another's ostrich, and another's fish. Okay, and you have 2 side dishes. Maybe one's mashed potatoes, another one's rice. And you have 5 desserts. I don't know, cookies, candy, ice cream, cake, and chocolate. All right, so a probability problem would say, well, what's the probability of randomly selecting a meal that consists of ostrich, mashed potatoes, and chocolate? All right, well, if there are 40 different possible meals, then the probability of getting any one of those meals is 1 out of 40. All right, but we'll get to that later. This is I just went through that to show you kind of what the relationship is between the counting principle and probability. Another example, within an area code, phone numbers have 7 digits. The first digit cannot be 0 or 1. How many possible phone numbers are there in a given area code? So let me give you a hint about how to set this up. I like to set it up with the lines indicating events. And in this case, the lines indicate the different slots where a digit can go. All right, and then once you kind of represent it visually that way, you can figure out how many different possible events would go into each slot. And so you can write that number underneath the slot. Okay, well, I've given you some hints. If I pause now, you should be able to figure out how many possible phone numbers there are in a given area code. So do that on your own and then resume when you have an answer. The answer then is 8 million possible numbers. And that comes from just 8 times 10 times 10 times 10 times 10 times 10 times 10. These are all considered independent events. We multiply them all together, and the result is 8 million. Now, just in case you're wondering about this 8 here, you know that for every other slot there are 10 possibilities. That's 0 through 9. Okay, so let's count on our fingers, right? 0, one finger. 1, it's my second finger. 2, third finger. 3, fourth finger. 4, fifth finger. 5, sixth finger. 6, 7th finger, 7, 8th finger, 8, 9th finger, 9, 10th finger. All right, so 0 through 9 are my 10 possibilities. And so that takes care of the 10. But since this first digit can't be a 0 or 1, then I have 2 possibilities less, and that's why it's 8. So 8 times 10 times 10 times 10 times 10 times 10 times 10 is 8 million. A permutation is an ordered arrangement of n different elements. How many permutations are possible using the three colors red, white, and black? All right, so red, white, black, black, red, black, white. These are different permutations, ordered sequences. And the question is, how many are possible with these three colors? Well, let's lay it out visually, and then we'll see the math behind it. So we know there are 3 choices for the first color, 2 choices for the second, and 1 choice for the third. In other words, if I have 3 blank slots and I need to fill them in with colors, and I just start out, I can choose anything. Well, I can choose red, white, or black for the first slot. But then once I've already assigned one of the colors to the first slot, I've only got 2 left. That's why there are 2 choices for the second. And once I assign something there, there's only 1 choice for the third. Okay, now let's see that in action visually. This is one possibility, another, a fourth possibility, a fifth possibility, and a sixth possibility. All right, and I can see that it ends up being 3 factorial. Now let's go through this visually. You could have just approached this problem by drawing everything. And luckily, since there are only 3 colors, you could have done it fairly quickly. But when you get to something like 10 colors, then it would take you a really long time to do it this way. But for the sake of clarity, let's just go through it visually first. All right, in the first slot here I have red. And I know that I can also have another possibility that has red in the first slot. So these 2 in the first row are possibilities in which red occupies the first slot. Well, the only 2 options then are red, white, black, and red, black, white. And those are the only 2 options, or 2 different possibilities if red has already been assigned to the first slot. In the second row here, I have white assigned to the first slot. And of course, if white's already assigned to the first slot, there are only 2 options for the other two slots, right? So I can have white, black, red, or I could have white, red, black. And finally, using the same logic, black, red, white, or black, white, red. And so these are the 6 different possibilities. Now mathematically it ends up being 3 factorial. And I think it's much easier to do it this way, because if I look at this 3, 2, 1, okay, if I look at this 3, 2, 1, all that means is for my first slot, I had 3 different possibilities. That's why I put 3 here. So that event, there were 3 different outcomes, possible outcomes for that first event, which is assigning a color to a slot. And then after a color is assigned to a slot, there are only 2 left. And that's why this second slot is 2 for the second event, which is assigning a color to the second slot. Choice of only 2. And then after I assign something to that slot, there's only 1 more color to choose from. And that's why there's 1 in this third slot. Okay, so going through it specifically, let's look at this 3, 2, 1 again. I've got red, white, and black. Let's say that I randomly throw in white here. Okay, then I've used up white. I had 3 possibilities, red, white, and black. I used up white, which leaves only black and red for the second slot. And let's say I throw red in there. Well, now I've used up 1 out of those 2, and so there's only 1 left, black. All right, so this accounts for the 6 permutations, and that is equivalent to 3 factorial. 3 times 2 times 1 is 3 factorial. The number of permutations of n elements is n factorial. The number of permutations of n elements is n factorial. So this red, white, black is a permutation. This red, black, white is a permutation. This white, black, red is a permutation. This white, red, black is a permutation. This black, red, white is a permutation, and this black, white, red is a permutation. There are 6 permutations. A permutation of n elements taken r at a time is a subset of the collection of elements where order is important. Okay, it sounds complicated. It's really not, and it becomes more clear when we see specific examples. For example, 5 projects are entered in a science contest. In how many ways can the projects come in first, second, and third? All right, this is where order matters, because if Johnny gets first, and Carol gets second, and Susie gets third, that's not the same as Susie getting first, Johnny getting second, and Carol getting third. All right, so order matters. And I can see I've got a subset here. There are 5 projects total, but the subset of prize winners is only consists of 3, first, second, and third. So this would be a problem of a permutation of n elements taken r at a time. 5 elements, that's my n, taken 3 at a time. That's my first, second, third prize winners. 3 different prize winners. Alright, so pause the video, try to figure this out on your own using factorials, and then resume if you get stuck or if you get the answer. Okay, so let's lay it out. First, second, and third, we've got our first place winner, our second place winner, and our third place winner. And I can write my little lines there to indicate events. Well, I've got 5 projects to choose from for the first place winner, 4 projects to choose from for the second place winner, and 3 projects to choose from for the third place winner. 5 times 4 times 3 is 60. So there are 60 different ways that I can assign first, second, and third places to a pool of 5 projects. And it makes sense to draw it as events, because it's clear that if I have not picked any prize winners yet, right, clean slate, all the projects have displayed, I'm a judge, and I'm going to assign prize winners. Well, clean slate, no one's a winner yet. That means for the first place, I still have all 5 to choose from. That's why I have 5 here. But then, once I assign a first place winner, I've only got 4 different candidates for the second place. And once I assign that, I've only got 3 different candidates for the third place. Okay, it becomes clear visually that it's 5 times 4 times 3. Independent events times each other, right, to get the total. So there are 60 ways, or 60 permutations for prize winners in this case. Now let's look at it mathematically. Okay, so the formula for the number of permutations of n elements taken r at a time is NPR. You can find this number on your calculators, or if you prefer, maybe you can't find it on your calculator or you prefer to do it another way, NPR simply consists of n factorial divided by n minus r factorial. Now this formula looks complicated, but it's really not, and we're going to see why it's really quite simple by applying it to our specific example from the last screen. Okay, so NPR specifically from the last screen is 5p3. 5 represents the number of projects, and 3 represents the number of prize winners, so 5p3. Well, it's 5 factorial over 2 factorial because my denominator is n minus r, which is, in this case, 5 minus 3, and 5 minus 3 is 2. Well, why do we have that denominator n minus r factorial? Well, the reason we have it is because I've only got 3 slots, okay, which I'm highlighting here with the arrow. And 3 slots means that for this first event I've got 5 to choose from, for this next event I have 4 to choose from, this next event I have 3 to choose from. Well, the 2 and the 1 cancel, numerator and denominator. So I'm left with 60. Alright, well, all this does is it shows that this mathematical formula, n factorial over n minus r factorial, is simply what gives you the more, I guess, common sense approach of the 5, 4, 3, which we already figured out on the last screen. Okay, so do write this formula down. You're going to need it. Again, you can use the NPR button if you want, You can just write out n factorial or n minus r factorial if you want. Or you could just do the common sense method of 5, 4, 3. It is, however, helpful to know the formula, especially for very large permutations, because then it'll be easier to do it on your calculator. Here's the classwork, page 698. Please write these numbers down, and we'll see you in class.